Hey guys, welcome to this video. So today we'll be looking at a physics concept. We'll be looking at this fish that's hanging on a string in an elevator, right? And we'll be sort of going through what happens as the fish or as the elevator starts accelerating upwards and starts decelerating or accelerating downwards. So we'll be going through what happens to the scale, whether the reading changes, because we already know the weight remains the same, but what happens to the weight as induced by the acceleration? Let's get into the video. So the first question we're being asked is we're being asked to show what happens when the elevator accelerates upwards or downwards. We're asked to show whether the reading on the scale will remain the same or whether it will change or whatever happens. So in physics, we go with formulas. You don't just make assumptions. So the first thing I'm going to do is I'm going to define my direction. I'm going to define the upward direction as my positive. Then everything that goes down or opposes the upward direction, which I've defined as my positive, will sort of be assumed to be negative. So an example I can give is weight, which is mass times gravitational force. So this, when the elevator is going upwards, this force will be taken to be negative because it acts downwards. When the elevator is going downwards, gravity will be taken to be positive. So to do that, we're going to utilize Newton's second law, which is summation of all forces in y is equal to the mass in y times the acceleration as well. And we're only considering the y-axis because there is no other force acting, there is no force in the x direction acting on this system. So we're only going to focus on the forces in y. So already we can tell weight is one of the forces acting on the scale, but another is the tension in the spring. Because as the weight is pulling on the scale or the spring within the scale, using through the string, there is a force exerted on the spring that is keeping the fish hanging. So that force will be called tension. And this tension, since it is the only thing that is stretching this rope to give a reading on the scale, this tension will be equal to whatever reading we have here. So the tension is basically what we're looking to find, right? Hopefully we are on the same page. So we only have two forces. Tension, weight or weight force is pulling downwards. So meaning it will be negative, of course. But the tension force is resisting the weight to keep the fish hanging on the string, if you get what I mean. So tension will be acting upwards. Since it's acting upwards, it will also be positive. So the forces in Y include the weight, which is negative, and the tension, which is positive. All this is equal to the mass times the acceleration. We already know it's in the y direction. So what we can do is now we can replace the weight with the actual values for the weight. That is, if we had them. But for now, what we can do is replace weight with mass and gravitational force, because that's what weight is standing for in this equation. But to know what happens to the spring, we're looking for the tension, because the tension, as we stated before, the tension is equal to whatever reading we have on the spring balance. So the tension will be equal to, just applying some basic mathematics here, the tension will be equal to the mass times the acceleration plus the mass times the gravitational force, which is the weight. And to simplify this equation further, we can say tension is equal to, we can factor out mass times gravitational force, which is the weight of the fish. Then we get mass times gravitational force into this. Mass obviously goes out, remaining acceleration over gravitational force plus 1. This is our formula that we'll be working with. Now let's do a bit of investigation. From what we can tell, the only thing that will be changing in this system is the acceleration. So if the only thing that will be changing in this system is the acceleration. So if the elevator chooses to accelerate upwards, our acceleration will be positive. If our acceleration is positive, this whole value is positive. You multiply that with the gravitational force. It should give a reading that is higher because you are multiplying it to the gravitational force, which is the actual weight of the fish. But you are multiplying all this, which is acceleration over gravity plus 1, which obviously, according to math and all the math rules we know, this should give us a value that's a bit higher. However, if we choose to decelerate, meaning our acceleration becomes negative, let me just remove that, means our acceleration becomes negative, right? And if our acceleration is negative, we should get a value that is smaller according to this formula. But let's investigate this using real figures to see what we get. You can pause it now. Okay, now we're dealing with a different question. We're going to work with figures to actually calculate this thing. Okay, my mic is working. So the question reads, evaluate the scale reading for a 40 Newton fish if the elevator moves with an acceleration of plus or minus 2 meters per square second. And that basically means they are looking for us to calculate the reading when the elevator is moving upward and downward, when it's accelerating upwards and decelerating. So that's just what we're going to do. With the formula we defined, we said tension, which is the scale reading, is equal to, that was mg acceleration over gravitational force plus 1, right? So the first thing we're going to do is just work with our data we have to calculate tension and then see what value we get. So in this case, tension is equal to the mass times gravitational force, that's the weight, and we've been given that the fish is weighing 40 newtons. So that's 40 newtons, which is the weight of the fish. The acceleration we've been given as 2. Since we're determining or working with a case where the elevator is accelerating upwards, we're going to use 2 meters per square second over the gravitational force, which is a constant, 9.8 meters per square second, plus 1, which is part of the formula. So when we do an evaluation, we're going to discover that this gives us 48.2 newtons, hence proving the fact that as the elevator goes upwards, the acceleration becomes, the weight of the fish in that particular moment becomes more than what it actually was. Now we're going to work with the opposite direction. We're going to work with deceleration, which is basically when the elevator moves or decelerates downwards at the same speed, the same magnitude of acceleration, but in the opposite direction, which is downwards. And according to the direction we determined, we basically said upward direction is positive, and anything happening in the opposite of this upward direction will be regarded as negative. Okay, so first of all, we go again with the formula. We have tension is equal to mass times gravitational force times acceleration over gravitational pull plus 1. Now let's see what happens as the elevator starts decelerating. So we'll have our tension, which is our weight. The mass times gravitational force again has been given to be 40 newtons. And our acceleration, since we're going downwards, will be taken to be, the negative part of the acceleration will be negative 2 meters per square second over 9.8, which is our gravitational pull, and that is a constant. It is not changing. Okay, and as we evaluate this, we discover that our acceleration becomes 31.8 newtons, hence proving the theory we had at the very beginning of this conversation, that as the elevator starts decelerating, it experiences, or the scale experiences less weight than is actually being induced by the fish.